All right, let's take a look at section 5.4. This is on a very useful type of concept in math. It's called a vector. It's also used a lot in many other disciplines, science, physics, places like that. Tons of vocabulary to go over here. So we want to make sure that we're clear on what each of these words mean. So let's start off by talking about what a scalar is. You've probably heard of a scalar before. You probably used that in your college algebra class when you were talking about matrices. But a scalar is a quantity that measures only magnitude. It only measures how big things are, and it's just a plain old number. So if we were to say something like 51 pounds or something like that, or we said we took a measurement and it was 2 feet, or we said the car was going 40 miles per hour. Those are all just scalar quantities. They just measure how big something is, a plain old number. Well, a vector quantity measures two things. It measures not only the magnitude, but it also measures the direction. So it's got two things. It's got a plain old number with a direction. So for example, if we said 51 pounds, but we said we applied that 51 pounds at an angle of 90 degrees or something like that. Or let's say we were going 40 miles per hour, but I added a direction and I indicated that we were going south. That would then qualify as a vector. And vectors are very useful. We're going to learn some applications of these in the next section in 5.5, but for now we just kind of want to get used to the notation, the vocabulary, how we can represent them and that sort of thing. So the nice thing about a vector is it's got a nice geometric representation. A vector can be represented as a directed line segment. So the length of the vector represents the magnitude. So how long we make the line segment will represent the magnitude of the vector. And the angle at which we draw the vector, that's going to represent the direction. Okay, so we've got some examples here. And again, we're just getting used to the notation and the vocabulary. Lots of notation, lots of vocabulary here. So it says, draw the vector from the point A, 0, 0, to the point B, 3, 4. And so that's really easy to plot those points. So I'm going to put A right here, and I'm going to put B right here, so over 3 and up 4, okay? And we've got to have a directed line segment. And the way we draw this is really important because we're directing this from A to B. So we're going to go from A to B, and the way we indicate that it's moving in that direction is we'll put a little arrow on the end there. So this is the vector AB. Now, the type of notation that we use, a lot of times we'll use several different types. So in this notation, what I'm going to do is I'm going to put a little line over it with a little arrow. So in the software that I use, it makes it look like that. So there's the vector AB. We could name it lots of different things. We could have named it vector U, in which case we would have put a little kind of a script V with a little arrow over the top of it. So there's vector V, there's vector U. You can also have vectors indicated, and some textbooks will do this. They'll make it a bold script letter if they want to indicate a vector. Most of the time we're going to have the little line over the top, or it'll be pretty clear. We'll name the vector. We'll say vector V so that you can't be mistaken. But this is what we've got right here. So the vector from A to B. Now, it's important to point out that this would not be correct. If I were to write A, B, and then put the arrow going the other way, or BA and put the arrow going that same direction. Okay, this would indicate that we're starting at B going toward A, and that's not what's happening here. So we want to make sure that we indicate that in the right direction. So we want to identify a couple of different points. We want to identify the initial point, the terminal point, and the magnitude. So let's talk about what the initial point is. The initial point is just like it sounds. It's the starting point. So in this case, the initial point would be A. The terminal point is the ending point, or where it stops. So in this case, that would be point B. And then the magnitude would represent how, let me write this, how long the vector is. Okay, so we can actually figure that out here. And if we just looked at that, I mean, we've done this type of problem numerous times, but we want to talk about how it's indicated also. So the way we indicate the magnitude of the vector, sometimes we'll just put it in what look like absolute value bars. But if we've got a vector in there, we know that we're talking about the length of the vector, or in other words, the scalar quantity that represents how long it is. Sometimes you'll see double absolute value bars. That's pretty common. And again, this kind of just sets this off and lets somebody know, hey, you're not just taking the absolute value of a plain old number, you're kind of taking the length of a vector. So if we were going to find that, we could come over here and we could say, well, I need to figure out how long this is, and I can do that by figuring out, well, this is 3, and this is 4, and I can have a little right triangle here, and I can use the Pythagorean theorem, and I end up with 5. So on this particular problem, the magnitude of vector AB is 5. And then we can talk about tip and tail. These are kind of informal terms that we use for this. The tip is the ending point. Okay, so the tip would be where the arrow goes. So in this case, the tip is B, and the tail is the start point. So in this case, the tail would be A. So it's kind of heading in that direction. This is the tip or the head of the vector, and this would be the tail. Okay. And then we want to talk about the direction angle, because remember, a vector measures two things. It measures the magnitude and the direction. So let's find the direction angle on this one, and we'll note that the direction angle is always measured from standard position. Okay, just like we're normally used to. That's what we've got there. So we want to find this angle right here. Well, there are lots of different ways to do that, but if I know I went 3 this way and 4 up to get from the tail to the tip, then I could figure out that the tangent of theta is equal to the opposite over the adjacent, or theta in this case is going to be the tangent inverse of 4 over 3. Okay, so I'm going to grab my calculator really quickly and we'll compute that. We should know roughly what we're looking for. I'm going to do this in degrees. So we should be able to take a good guess at what we're going to get here. So let me change the mode here, put this in degree mode, come back here, clear all this off. This is a larger opposite side than the adjacent side is. So we're expecting an angle that's a little bit larger than 45. So I'll do tangent inverse 4 divided by 3. And in this case, I end up with 51.3 degrees. Okay. So this is 51.3 degrees. So here's our magnitude of 5, and here's our direction of 51.3. Okay, so a little bit of practice in getting used to those. So again, we've got our tip right here, we've got our tail right here, our starting point and our ending point. We've got our magnitude of the vector right there, and then we've got our direction angle. So lots of vocabulary to get used to. And we're going to use that vocabulary in the next case to talk about when vectors are equal. So vectors are equal if and only if they have the same magnitude and the same direction. So both of these things have to be equal in order for vectors to be equal. And we're going to look at some couple of different vectors here. We'll just plot these. So I've got some points written down here. And then we want to plot vector A, B, C, D, E, F, and so forth, given those measurements right here. So we've got A right here and B right here. So this is the one that we were talking about before, okay? And I'll do that one in red. So this is A and this is B. So there's vector AB. Then we're going to do CD. CD goes from 4, 7. To 1, 3. So 4, 7. So here's 4. Okay, we're up right there, about right there. So there's C, and then D is 1, 3. 1, 3 is about right here. So we're headed in this direction. Again, indicate that directed line segment. We can see how long it is and which direction it's headed. Okay, and then we've got EF. So we've got 2, negative 1. So over 2 and down 1. So that's where our tip is, and or sorry, our tail is, And then our tip, the direction we're pointed, is 5, 3. So I'm going to be at 5 and 3. So we're right here. Again, this is E, and this is F. And we head off in this direction right there. So we'll indicate that with putting the arrow at the tip there at the head of the vector. And then we've got GH. So GH is -4, 1. So back 4 and up 1. And H is -6, 4. So we're going to be about right here. So this was G, and this is H. And we're headed off in this direction right there. So again, we're just geometrically representing these 4 vectors. We can see each one of them has a definite length, and we can see the direction indicated by the arrow. And now we've got this question here that says, state which vectors are equal. So if we take a look at these, we've got a couple that look like they're roughly the same length. Okay, clearly that one's not the same length as the other ones are. Okay, but not only do they have to be the same length, they've got to head off in the same direction. So even though these look like they're the same length, there's no way that vector, oops, let me label this here. There's no way that vector CD could be the same as vector AB, because clearly they're headed in opposite directions. Okay, so the only ones that could possibly be the same are these two right here. And let's just double check and make sure. We already figured out that the magnitude of vector AB was 5. Okay, we went over 3 and up 4. And so we could figure out that angle right there, that direction. And keep track of this, because this is also a nice way. If we've already got it geometrically represented, this is a nice way to tell whether or not they're headed in the same direction. I went over 3 and up 4 to get from the tail to the tip. Let's check this one right here. Okay, I'm going to go over 1, 2, 3 and up 1, 2, 3, 4. So over 3 and up 4 on each one of those. So this vector would also be 5 units in length, and if we were to compute that direction angle, it would also be the same. So the two vectors that are the same are vectors AB and vector BF. Okay, those two are equal to each other, okay, because they have exactly the same magnitude. They're both 5 units in length, and they're headed in the same direction. If we were to check this one right here, okay, this one would work out to be, this would be 3 and this would be 4. It's going to work out to be 5 units in length. But again, you'll notice that the direction angle, if we measured that from standard position, there's no way that this angle right here is the same as this guy right here. Okay, and we'll talk more about those direction angles a little bit later. Okay, so one of the things that's nice about vectors is you'll notice if I take them and I slide them around, it doesn't change the magnitude and it doesn't change the direction. So if I just take any one of these, let's say I take this one right here and I slide it, let's say I slide it so C is at the origin. So it would head off in exactly the opposite direction. It would look about like that. Okay, sliding it around, as long as I move the entire thing the exact same amount, doesn't change the magnitude, and it doesn't change the direction. It's still 5 units in length, and it's still pointed off in this direction right here. Okay, so again, I've just kind of demonstrated that the easiest way to do this is to slide it so the tail is at the origin. And if we slide it so the tail is at the origin, we get a couple, well, we've got a couple names for this, but it's called a position vector or a radius vector. And the reason that position vectors are nice is because it makes it really easy to compare vectors, since they'll all start at the same place. Start at the same point, we'll say. If they start at the same point, then it's going to be really easy to tell, do they head in the same direction, and do they have the same magnitude? Are they the same length? Okay, and this leads us to the idea of component form of a vector. Component form of a vector. Now, the reason why component form is so useful is because it allows us to represent a vector and write a vector using only 2 pieces of information. We're going to have the horizontal component and a vertical component. And that's why it's called component form, because we just got those 2 components, a horizontal component and a vertical component. And component form looks like this. It's got angle brackets, so it kind of differentiates from the point AB by having an angle bracket on each end. Okay, so A is going to be the horizontal component. Think of that kind of like in the x direction, the horizontal direction. And B is going to be the, whoops, I've got, I need to change this. Oops, that should say vertical. Okay, so A is the horizontal component and B is the vertical component. Okay, all right. So we could actually represent, let's take a look at vector A, and let's represent that in horizontal and vertical components. So remember, we went over 3 units, and then we went up 4 units. So that's going to be 3 for a horizontal, 4 for a vertical. So vector A would be 3, 4 in component form. All right. And let's look at the next page and look at an example here. It says, write the vector AB, so new points A and B, in component form. So if we were to draw this vector, let's draw what this looks like. So vector A is -2, -1, or sorry, point A is -2, -1, and point B is 2, 4. So we're right here. Okay, so that's what the vector looks like. Okay. Now, if we've got a graph and we can draw it and all that good stuff, then we're in pretty good shape. It's still very easy to work with, but it would be nice if we could represent this in a format that doesn't require us to graph this. So here's the easiest way to do this. The best way to accomplish writing a vector in its as a position vector, or as a radius vector, we sometimes call it, is subtract the tail from the tip. So we're going from A to B. So this is the tip, and this is the tail. Now, I'm going to go ahead and do that, and we're going to put this in component form by taking the tip and subtracting the tail. And what I do there is I do that coordinate by coordinate. So I'm going to take 2, and I'm going to subtract -2. And I'm going to take 4, because that's this component of the, or this y coordinate, if you want to think of it that way, for the tip. And I'm going to subtract the tail. Okay. So this ends up being, let's see, we've got 2 minus 2. So this is 4, comma, and then I get 5 out of this one right here. So if I represent that vector as a position vector, this is what I get. I get 4, 5. Well, take a look at what we did. Okay, what we just did here is we basically just slid this over 2 and up 1. So we're going to start right here. If I go over 2 and up 1 here, I'm going to take this one and go over 2, and I'm going to go up 1. So this is my new tail, again at the origin, so that it's in standard position. Okay, so we've got our position vector here. And then this is where it's going to end up. So if I draw that, you'll notice that it's the same length. It's still heading in the same direction. Mine looks like it's a little bit off, so let me redo that. So we're headed in exactly the same direction, and it's exactly the same length. Okay, so taking the tip and subtracting the tail basically slides this over wherever it is, so that the tail will be at the origin, and that will produce our position vector for us. Okay, so example 3 star says, find the magnitude of AB, and again, this is the way we'd write this, and the direction angle. So let's go ahead and do this. And this is the nice thing about having this as a position vector. I've already got standard position right here. I just need to measure that angle, and I need to know how long it is. So here's how we do it if we've got it in component form. This is 4, 5 in those angle brackets. And if I were to think about how do I actually go through and I find the magnitude, how long this is, well, think about it. What we did on the last problem is we took this and we said, all right, well, let's figure out how far we went over this way and how far we went over this way. In this case, I went over 4 and I went up 5, and then I used the Pythagorean theorem. Well, the great part about this is I can just do this using the Pythagorean theorem. So if I wanted the magnitude of AB, I'm going to take 4 and square it. That's the horizontal part. I'm going to take 5 and square it. That's the vertical part. And I'm going to take the square root. So if we generalize that, let's say we had the vector u. So it's got two pieces, u1, comma, u2. So that's the component form for that vector. Then the magnitude of that vector would be the square root of square the horizontal component and add it to the vertical component squared. And that's how we'd find the magnitude. So in this particular case, I get 16 plus 25. So I get, what do we got here? Radical 41. Okay. So there's the magnitude, and that would be our exact answer. And then if I want to find this direction angle right here, so the next thing I want to do is I want to find that angle right here. Okay, so we figure that out. Well, we did that on the last problem, and we did that using a tangent. So that angle, the tangent of that angle in standard position is going to be 5 over 4. Again, we're expecting an angle that's going to be a little bit larger than 45. So theta is going to be equal to the tangent inverse of 5 over 4. So let's get what that is. So I'll hit second enter, recall that, edit that, 5 over 4, and I get 51.3. So this is 51.3 degrees. So there are my two answers in this particular case, but let's think about how would I do that in general? Well, the cool part about this is you'll notice that in each case I get the vertical component over the horizontal component. So I could find the angle by just doing tangent inverse of the vertical component over the horizontal component. So in this case, I'm going to put u2 over u1. Okay, so here's a nice formula for figuring out the magnitude of a vector, and here's a nice formula for figuring out the direction angle for a vector. Now, as we do most of the time in math, we learn how to do something and then we learn how to do the opposite. So what we did here is we had component form, and we took this and we figured out the magnitude and the direction angle. Well, what if we wanted to find component form for vector v? Notice how that's indicated, given that the magnitude of vector v is 5.6 and the direction angle is 22. So let's think about what that would look like. So I'm going to draw a picture. We've got 22 degrees, so about like that, and this is 5.6. So here's vector v, and this is 5.6 units long, and this is 22 degrees. And what we want to find is, we want to find what this is in component form. So I want to figure out this, and I want to figure out this right here. And that's my question, okay? So I'm going to use something that we're used to doing. I'm going to say, well, I don't know what this is. I'm going to call that one x, and I'm going to call this one y. Or I could call this v1 and v2. Wouldn't really make much difference. So here's what I do. If I want to figure out what x is, I've got the angle and I've got we could call this the hypotenuse or the radius. So that would mean that the cosine of 22 degrees should be equal to the adjacent side, which is x, over the hypotenuse, which is 5.6. So x is equal to 5.6 cosine 22 degrees. And I could figure that out. Let's throw that in the calculator. See what we get here. So this is 5.6. and then cosine 22 degrees. Had that in degree mode, so I get 5.2. 5.2. And then we're going to compute what y is. Well, that would be the opposite side in the hypotenuse. So this is going to be the sine of 22 degrees is equal to y over 5.6. So 5.6 times the sine of 22 should equal y, and let's figure that one out. So all I need to do is change this to a sine, and there's my answer. So 2.09, 2.1 if we wanted to round. So 2.1. So in component form, vector v would be equal to 5.2, again rounding, 5.2 comma 2.1. There's the horizontal component and there's the vertical component. Okay, well, if you think about it, what we did on each one of these is to find the horizontal component. We took how long this was. Okay, we took the radius or the magnitude, and we multiplied it by the cosine of the angle, and that gave us the x-coordinate. And for the horizontal component. And the vertical component, we took the magnitude, or the radius right here, and we multiplied it by the sine of the angle. So if you think about it, we could write down a general formula, and that general formula would look like this. It would be the magnitude of vector v times the cosine of the direction angle. And the y-coordinate, or sorry, the vertical component would be the magnitude of vector v times the sine of theta. And that should look really familiar, because you'll remember when we were working on the unit circle, we always said that on the unit circle, the cosine of the angle is the x-coordinate, and the y-coordinate was the sine of the angle. And if we were to make that larger, all we'd have to do is do r cosine theta and r sine theta. This works if it's 1 for a radius, and this works if it's any radius. So we can kind of see some analogies right there. Okay, let's talk about some more vocabulary here. So let's talk about scalar multiplication. So when we do scalar multiplication, we're going to multiply the vector by a scalar, by a plain old number. And what this can do is it can make the vector longer if we're multiplying by a vector or a scalar that's larger than 1. It can make it shorter if we're multiplying it by, a fraction or a decimal that's between 0 and 1. We could make it the exact same length by multiplying it by a 1, and we can even make it go the opposite direction. So you might want to think about how that would happen. It's got to have something to do with the value of that scalar and the sign of the scalar. So let's take a look at this, this problem right here. We're going to do 2 times the component vector 3, 4. Well, it's literally this easy. All you have to do is multiply it by component by component. That scalar essentially gets distributed through to each one of those. So what we've got here is we've got the new component form would be 2 times 3, 2 times 4. So we'd have 6, 8. That's it. That's the answer. Okay? If we were to multiply this by -2, the answer on this one would be -2, -2. And if we multiply this by a negative, we end up with -1, -1. So those are the answers to each one of these, and it's a good idea to think about geometrically what happened here. So let's work backwards on this one. So this original vector was horizontal component of 1, vertical component of 1, so it was heading off in this direction right here. When I multiplied it by a negative, here's what happened. It doesn't change the size of either one of these components, it just changes the sign. So instead of going to the right, I'm going to go to the left, and instead of going up, I'm going to go down. So you'll notice this is heading in exactly the opposite direction. It's still the same length, but just headed in the opposite direction. Let's think about what this one does. This one, again, is the vector 1, 1. This would be -2, -2. So it's going to head in the opposite direction. That's what the negative did. Multiplying it by 2 made it twice as long. And if we were to look at this one, I'll have to keep this relatively small, over 3 and up 4. Okay, there's that vector. There's the original vector, 3, 4. If I multiply it by the scalar 2, then here's what we end up with. We end up with 6 8. So there's 4, 5, 6, 5, 6, 7, 8. So we're right about there. It's twice as long, but heading in exactly the same direction as the original one. Okay? All right, now let's talk about vector addition. Vector addition is something that we're going to do quite a bit of, and we're going to find some applications of this. So we can add 2 or more vectors, and what we get when we add 2 or more vectors is we get what's called a resultant vector, or just the result of adding those vectors together. You can kind of see where they came up with the name. So there are a couple different ways that you can do this. We can do it geometrically these 2 ways, using the tail to tip method, or we can use the parallelogram method. Okay. Now I've got here a third technique, and that's by doing it in component form. The nice thing about component form is all you need are the components, and then you just perform the operations. And I'll show how that's done, but we are going to look at this geometrically because it is valuable to understand how these are put together. So we're going to take vector u, which is 2, 3, and vector v, which is 5, -2, and we're going to figure out what the resultant is. So let me show you how this is going to work. I'm going to do this one in red, and I'm going to do this one in blue. So I'm going to take vector u, so let's draw what that looks like, 2, 3. Again, this is a component vector, so we've got our position vector here. So over 2 and up 3. So here is vector u, okay? Vector v looks like this. It's 5, -2. So over 5 and down 2. So it's going to look like this, headed off in this direction. And what we want to find is, what is the result of combining the two of those together? Okay, so that's what we're after here. Well, here's the parallelogram method, and there's nothing wrong with either of these methods. They're both very good. I'm going to show you the parallelogram method first. I'm not a huge fan of the parallelogram method, but we'll go ahead and do it. So what we do to do the parallelogram method is I take a copy of this one and I draw it over here. So I'm just going to draw it straight over here. So it's going to look something like this. Okay, and you have to be pretty accurate about this. So I've drawn a copy of this red vector u over here, and then I'm going to draw a copy of the vector v. So that's going to be over in this direction. And you've got to be pretty darn careful about how you do this. Notice that we went over 5 and down 2. I'm going to go over 5 and down 2. And here's where the resultant is. The resultant is the vector that goes from the tail of both of them to the tip of both of them. Okay? So this right here is r. So if I take u and I add v, I get r. So I'm looking for this guy right here. Okay? All right. So let's figure out where we are there. Well, where we are, notice that this vector r starts at 0, 0. So it's already a position vector, and it ends right here. Well, let's see. We went over 2 for this one, and then we went over 5 more. Okay, so that puts us at 7. So this point here is, let me do this in black. This point here is 7, comma, and then we were up at 3, okay? And then we went down 2 for this one right here. So we end up at 7, 1. So since that point is where it ends and it starts at 0, 0, that is the answer. The answer to this one is 7, 1 in component form. Okay? And again, that works totally fine, works very well. What I like to do is I like to do the tail to tip method. Okay, so let me erase this and come back here and do the tail to tip method. So the tail to tip method works like this. Draw the first one and then put the tail of the next one starting at the tip of this one right here. So I'm going to put a little set of axes right here. And then I start right here and I go over 5. So 1, 2, 3, 4, 5. And then I go down 2. 1, 2. So I end up right there. So this is vector v. And the resultant goes from the tail of the first one to the tip of the second one, so it ends up like this. Okay, and we end up doing the same thing. You'll notice that all I didn't draw was just the original vector v here and the copy of vector u right here. I find that to be a little bit easier. We still end up in the same place, 7, 1. So it's really personal preference. So the nice thing about this is you'll notice that I can do this in component form, and I literally take these and I take 2, 3 and I add 5, -2. I literally add the components together, so that's going to be 7, and that's going to be 3 plus -2, so that's going to be 1. So same answer. This is how we geometrically represent what's going on, and that's how we can get it very quickly. So you can see the advantage of using component form. Let's do one more and see where we're doing at that point. So vector u, again, is the same vector, 2, 3. So it looks like this. So there's U. And I'm going to do this one just using the tail to tip method. So I'm going to subtract two V's. Well, remember what the negative does to this. Okay. What it's going to do is it's going to change the direction of this. So I'm going to take negative 5 and positive 2. So I'm going to go back 5. 1, 2, 3, 4, 5, because we're subtracting this. And then we'd normally go down 2, but we're going to go up 2. So this is the opposite of vector v. Okay, so let me write down really what's going on here. We're taking u and we're subtracting v, then we're subtracting v again. So you'll notice that the v that I've drawn here is really a minus v. It's a vector v that's heading in exactly the opposite direction. So if I do that again, tail to tip, I'm going to go back 1, 2, 3, 4, 5, and then I'm going to go up 2. So there is another minus vector v. So here's vector u, and then I've subtracted 2 vector v's, and the resultant starts at the tail of the first one, ends at the tip of the second one. So we're going to end up right here. Now, this is a bit of a pain because you've got to make sure that you've counted correctly and graphed things correctly and stuff like that. But let's just go ahead and count. Okay, if I was at this point right here, which is 2, 3, and I back up 5 and go up 3, that would put this point right here at negative 3, up 2, so that would be 5. And if I back up 5 more, that's going to put me at negative 8, and then up 2 more, 7. So that's where we think that point is. So that means the resultant would be in component form, back 8, horizontal component of negative 8, vertical component of 7. So you can see that geometrically, it's a little bit of a pain to put these together. Heck of a lot easier if we just did this. So let's double check and make sure that we got this right. 2, 3, and then we're going to subtract in component form 5, negative 2. So this is going to be 2, 3. And then I'd subtract, this would be 10, and this would be negative 4. Suppose if you wanted to distribute that through and make that 2, 3, and make this a plus negative 10, 4, that would be okay. Either way, we're going to have 2 minus 2 minus 10, that's going to be negative 8, and then 4 minus a minus 4, so that's going to be 7. So same answer either way. But those are geometric representations of how we do those vector addition, or in this case, subtraction problems. And again, when we're subtracting, what we're doing is we're just adding the opposite there. So again, geometric representation of taking u and adding v, okay? Taking u and subtracting 2 v's right there, okay? So again, notice that the let's go back here and take a look at example 3. It says, notice that the original vector is the sum of the horizontal and vertical components. So let's go back and look at example 3. So this one right here. Again, I went 4 units this way and 5 units that way. So I literally took this vector that was 4, 0, and this vector that didn't go right or left, just went up 5, and we can add the two of those together. So if I take 4, 0, only a horizontal component of 4 and no vertical component, or 0 for a vertical component if you want to think of it that way, and then this vector right here, 4, 0, and 0, 5, if I add those together, this is the vector that I get. So I get 4, 5. There's the first one. Put the tail of this one at the tip of the other one, and then here's the resultant right here. Start at the tail of the first one, end at the tip of the second one. That would be another way to look at it in component form. Okay. I'm going to stop the video here in just a second so that you can kind of work on that. There are a few problems that you can do on the homework assignment at this point. Let that sink in. Maybe go back and look at your notes a little bit. If you're ready to go on with the next section, as soon as I'm done with this, think for a couple minutes and then go ahead and pick up on the next part of the video. So we can kind of summarize what we've been doing here. If we've got vector A that's got a horizontal component of A1 and a vertical component of A2, and vector B, B1, comma B2, and K is a scalar, then we can find what we call a scalar product, or in other words, scalar multiplication, by just distributing that through, as we saw up above. If we're going to add them, we literally add component by component, and if we're going to subtract them, we subtract component by component. Okay, so those are pretty straightforward operations. Again, this is just going to make it k times longer or shorter, depending on what the value of k was. We're going to add the components together and end up with the resultant. Very easy to do if you've got it in component form. And then the next thing we're going to talk about is something called a dot product. And dot products are very interesting, and we'll pick that up in the next video. So thank you very much.